Welcome to aminacademy.com. In physics, let us discuss about kinetic theory of gases. The kinetic theory of gases is a simple, historically significant classical model of the thermodynamic behavior of gases, with which many principal concepts of thermodynamics were established. The model describes a gas as a large number of identical submicroscopic particles like atoms or molecules, all of which are in constant, rapid, random motion. Their size is assumed to be much smaller than the average distance between the particles. The particles undergo a random elastic collision between themselves and with the enclosing walls of the container. The basic version of the model describes the ideal gas and considers no other interaction between the particles. The kinetic theory of gases explains the microscopic properties of gases such as volume, pressure, and temperatures, as well as transport properties such as viscosity, thermal conductivity, and mass diffusivity. Due to the time reversibility of the microscopic reversibility, the kinetic theory is also connected to the principle of detailed balance in terms of the fluctuation dissipation theorem, that is Brownian motion, and the Onsager reciprocal relations. Historically, the scientific theory of gases was the first explicit exercise of the ideas of statistical mechanics. Here, further we'll discuss about Boyle discovered the law named after him in 1661. Boyle, Newton, and several others tried to explain the behavior of gases by considering that gases are made up of tiny atomic particles. The actual atomic theory got established more than 150 years later. Kinetic theory explains the behavior of gases based on the idea of the gas consists of rapidly moving atoms or molecules. This is possible as the interatomic forces, which are short-range forces that are important for solids and liquids, can be neglected for gases. The kinetic theory was developed in the 19th century by Maxwell, Boltzmann, and others. It has been remarkably successful. It gives a molecular interpretation of pressure and temperature of gas and is consistent with Gas law and Avogadro's hypothesis. It correctly explains specific heat capacity of many gases. It also relates measurable properties of gases such as viscosity, conduction, and diffusion, and molecular parameters, yielding estimates of molecular size and masses. This chapter gives more explanation in detail. Next, we'll discuss about molecular nature of matter, that is Dalton's atomic theory also. As per Dalton's atomic theory, any compound has a fixed mass proportionality of its constituents, and when two elements combine to form a compound, the masses of other elements are in ratio of small integers to a fixed mass of one element. Now, we'll discuss about further molecular nature of the gases. We know that molecules which are made up of one or more atoms constitute a matter. In solids, these atoms and molecules are rigidly fixed and space between them is very less of the order of few angstrom and hence they cannot move. In liquids, the atoms are not rigidly fixed as in solids and can move around. This enables a liquid to flow. Suppose consider this is a solid, this is a liquid, and this is a gas. In gases, atoms are free to travel without colliding for large distances, such as that if gases were not enclosed in an enclosure, they would disappear. The average distance a molecule can travel without colliding is called the mean free path. The mean free path in gases is of the order of thousands of angstrom. In solids and liquids, the closeness makes the interatomic force important. The force has a long-range attraction and a short-range repulsion. The atoms attract when they are at a few angstrom but repel when they come closer. In gases, interatomic forces can be neglected. Next, we will discuss about behavior of gas molecules, kinetic theory, Boyle's law and Charles' law. Here, behavior of gases and molecules regards the kinetic theory as well as the laws of inert gases, ideal gases. The kinetic theory of gases is a simple, historically significant classical model of a gas thermodynamics behavior that laid the groundwork for many fundamental thermodynamic notions. A gas is described by the model as a vast number of identical submicroscopic particles like atoms or molecules moving in a random constant motion. Their size is thought to be substantially smaller than the typical particle distances. The particles collide with one another and with the container enclosing walls at random elastic collision. Now we will discuss about what is a gas. One of the four basic states of matter we know that is gas. The others being solid, liquid and plasma. A pure gas can be made up of individual atoms such as a noble gas like neon, elemental molecules such as oxygen, or compound molecules composed of variety of atoms. Example, carbon dioxide. A gas mixture such as air consists of several different pure gases. The gaseous state of matter exists between the liquid and plasma phases, with the latter serving as a upper temperature boundary for gases. Now, the gases are classified as ideal gas, non-ideal gas or real gases. Now, further we will discuss about kinetic theory of gases. The kinetic theory of gases is used to explain the behavior of gas molecules at the macroscopic level. It is study of gas molecules. There are 5 postulates of kinetic theory of gases are as follows. Gas is made up of a vast number of molecules that are constantly moving at random. Because of the distance between gas molecules is higher than the size of the molecules, the volume of the molecules is negligible compared to the volume of the gas. Intermolecular interaction are likewise insignificant. Molecule collisions with each other and with the container's wall are always elastomeric. Elastomeric means it's returned back with original velocity. The average kinetic energy of all the molecules is depending on the temperature. If temperature increases, kinetic energy of the gas also increases. The factors affecting the behavior of gases. Here, the following are the factors that influence gas behavior. Of course, it's a temperature, volume, pressure, quantity, that is number of molecules in the container. The component listed above are interconnected and are listed as follows. The volume of the gas expands as the temperature rises due to expansion of the gas molecules. Due to the contraction of gas molecules as the temperature drops, the volume of the gas reduces as well. Due to expansion of gas molecules as the temperature rises, the pressure of the gas rises as well. Due to the contraction of gas molecules, when the temperature drops, the pressure of the gas drops as well. The temperature of the gas must be very low or the pressure of the gas must be very high to transform it into a solid or liquid. When the quantity reduces, the pressure decreases, and when quantity grows, the pressure increases in the closed container. The volume and amount of the gas should be reduced to reduce pressure. To increase pressure, the volume and amount of the gas must be increased. Now let us discuss some important laws, gas laws. First, Boyle's law. When the amount of gas is fixed at a constant temperature, Boyle's law states that the volume of the gas is inversely linked to a pressure. That is, pressure is inversely proportional to volume by using cross multiplication PV equal to constant, because proportionality becomes a constant here. Therefore, P1 P2 V1 V1 equal to P2 V2 equal to P3 V3 is a constant, where P is the pressure of the gas and V is the volume of the gas. In PV diagram, the Boyle's law shows like. Next, Charles' law. The volume of a gas with a fixed mass is linearly proportional to the temperature. According to the Charles' law, V is proportional to T, where T is the temperature of the gas and V is the volume of the gas. Now look at here, that is in T and V with the x and y axis, then P is the constant. This is Charles' law. Gay-Lussac's law. When the volume of the gas remains constant, Gay-Lussac law states that pressure of a given mass of the gas varies directly with the absolute temperature of the gas. That means P1 over T1 is equal to P2 over T2, where T1 is the initial temperature and P1 is the initial pressure, T2 is the final temperature, P2 is the final pressure. Here this is a pressure and temperature when volume is constant. This Gay-Lussac law states like. Avogadro law. When the pressure and temperature of a gas remains constant, Avogadro's law states that the number of moles and volume of the gas are proportional. V is proportional to number of molecules, that is moles. Here V is proportional to N, or V over N equal to K, where V is the volume of the gas, N is the number of moles, and K is the proportionality constant. Here volume and number of moles is direct proportions. Now we'll derive ideal gas law from above laws. According to the ideal gas law, the product of pressure and volume of 1 gram of molecule is equal to the product of the number of moles of the gas, the universal gas constant and the absolute temperature, P equal to nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of the gas, R is the universal gas constant. It is 8.3145 joules per mole per degree Kelvin. T is the temperature of the gas. Now Avogadro's number is 6.0221 into 10 raised to 23 approximately. Now ideal gas properties and its characteristics. Ideal gas motion along the straight line is both constant and random. Here moves straightly, go and back, front and back, up and down, anywhere else, left and right. Here ideal gas movement along straight line is both constant and random. Because of the particles in the gas are so minute, the gas take up very little space. There is no interaction between the gas particles. Particles only collide automatically with the container walls and each other. That is why pressure created. The absolute temperature is directly proportional to the average kinetic energy of the gas particles. Many of the same particles, atoms or molecules make up the gases, which are perfectly rigid spheres that are also incredibly small. Because the volume of the gas molecules is so small in comparison to the space between them, they are referred to as a point mass. So far we had explain about gas law and ideal gas law and characteristics of gas and its properties. We have done. Please subscribe our YouTube channel.